Good morning all. The topic for today's discussion is glass transition temperature. Now, glass transition is a physical property of food polymers. It refers to a range of temperature over which the food polymer will change phase from a rigid, glassy structure into a more rubbery or soft state. Now, the food polymers that we are talking about can be proteins, starch or non-starch polysaccharides also, which may be cellulose, glucans, among others. Now, this physical transformation that we are talking about here results in a state where there is increased molecular mobility and increase in kinetic energy as well. Now, this glass transition, does it happen in all the molecules? No. Does it happen in every substance? No. It happens only in amorphous substances. Now, amorphous solids are formed by rapidly cooling a liquid melt or supersaturated solutions to a temperature such that the molecules do not have the time to rearrange themselves. As a result, what happens? They freeze as is where is. That is, they get frozen wherever they are present. Now, the amorphous solid that results is known as the glass. So, this glass liquid transition or glass transition happens usually upon heating. To arrive at the definition of glass transition, we can say that glass transition can be defined as the temperature at which an amorphous system gets converted from a glassy or rigid state to a rubbery state. We should not get confused between glass transition and melting. These two are entirely different phenomena. Glass transition happens only in amorphous solids, whereas melting happens in crystalline solids. Now, generally crystalline solids do have some amount of amorphous portion. Now, every crystalline polymer that you see will definitely have a portion of amorphous nature as well. So, the amorphous portion of a crystalline solid will also undergo glass transition. It will usually comprise around 40 to 70% of the total food polymer depending upon the type of polymer it is. So, when you talk of a polymer, food polymer as such, it will have a glass transition temperature also and a melting temperature as well. But one thing you have to get it clear is that the amorphous portion will undergo glass transition and the crystalline portion will exhibit melting properties. Now, certain substances are used above their glass transition temperature, certain substances are used below the glass transition temperature. This glass transition temperature that I am saying is denoted with the term Tg. So, when a substance is cooled below the Tg, what happens is the molecular movement that we are talking of, it gets reduced because the molecules are getting frozen and the molecular mobility gets completely affected. Similarly, when you are going to increase the temperature, that is when a solid is going to be heated above the glass transition temperature, what happens is the molecular mobility increases to an extent that you get a viscous liquid. Certain substances like water and glucose, they affect the plasticization of amorphous materials. Now, this is a term which I am using now. I'll tell you what that means as well. The water which is present in food generally functions as a plasticizer. Now, plasticizer is a small molecule. The role is that it will get in between the molecules of the substance and kind of space it out. As a result, what happens? The free volume increases. When this happens, the molecules are able to slide over each other in the substance. When water molecules occupy spaces in between the molecules of the substance, the resultant molecules are able to slide over each other more easily, which means at a lower temperature itself, this movement is possible, which should otherwise not be possible in the absence of the plasticizer. So, the ability of water to bring about this change is what is known as plasticization. So, the transition temperature or the Tg of a material can be lowered to make the material more pliable and easy to work with, and that is how we'll see that it is very useful in food products. Now, how can you actually trigger glass transition? It can be either using water or temperature. Now, the glassy material which has a region of very limited water mobility, because obviously there is no space for the molecules to move around. When you subject to heat, that is when you're increasing the temperature, or when you are adding water, in case of as in hydration, you will find it is getting converted to a rubbery material. The reverse is also possible. So when it is getting converted into a rubbery material, you find that the mobility of water is much higher here. Further heating, that is heating beyond this transition temperature, is going to make the resultant compound more fluid and viscous. One thing that you have to clearly remember is the terms like glassy and rubbery that we are using. These are only descriptive terms, and they are not talking about the eating quality of the product. You should not think you have a product which is rubbery. No, it is just used to denote the phase change from glassy to rubbery, and does not indicate or specify the texture or eating quality of the food material. All right. So I just told you that glass transition can be triggered either by water or by heat. We'll just quickly see a couple of examples for both. So for glass transition mediated by water, you have sprouting or malting. Now in sprouting, say for example your wheat kernels, we know they are very hard. Now when you add water to it, as is the case in process of steeping, you find that the water softens the kernels. So technically there is a transition happening there. You can think of your hard kernel as being that glassy material, and the addition of water kind of softens the kernel. And there is no change in temperature happening here. Another example is dough mixing. We know in dough, flour is the most important ingredient. It has both starch and proteins, predominantly gluten. So when you add water, water acts as a plasticizer and provides that molecular mobility. As a result, you get a dough. The flour will be your glassy phase that you are talking of, and the resultant dough will be your rubbery phase. Again, it is the phase I am denoting and not the texture. Glass transition mediated by temperature, your baking is the classic example, and freezing as well. Baking and cooling. Now when you bake, I'm sure most of you would have at some point baked cakes. So what happens is, when you bake, you definitely find, you see that the dough is getting converted into a, say if it is a cake, into a lovely cake. What happens is the starch gets completely gelatinized, and the proteins which are present, they coagulate. So the resultant product is a porous matrix which we get. Upon cooling, this starch which had gelatinized, it will retrograde, and what you get is a resultant rubbery state. Now freezing, again here bread is a very good example. Bread is a product which has high water content, moisture content and water activity. So if you want to improve the shelf life and you refrigerate your freeze the bread, what happens is that, again it is a example for glass transition here. So it is the temperature change which is driving the change that is happening. We'll see a couple of common examples in foods which you will be able to relate to, so that you understand the concept better. Best example is a cone ice cream. I'm sure all of you have had a cone ice cream at some point in your life. No matter how fast you eat, definitely the cone gets mushy towards the end. That is glass transition for you. The other examples would be chips. If your chips turn soggy, you find that they are indeed very hard to bite, they become rubbery. That is another example of glass transition that's happening. Your stingy, cheesy pizza, cereals with milk, all that you consume, these are also examples of glass transition. And also, if you leave salt open, you find that after a period of time, it absorbs moisture from air and it becomes liquid. So how do these manufacturers of salt make sure salt remains salt and does not turn into a liquid? That is something for you to ponder and find out. Now that we have seen what glass transition is, we will try and see how or what is the role in food industry. Now it is relevant to many food technologies which focus on providing improved shelf life to amorphous products. Now, apart from that, in many processes like freeze drying, spray drying and frozen foods, in candies, encapsulation and other processes such as agglomeration and crystallization, you find that glass transition has a very important role to play. For example, pasta. Pasta is usually marketed in the dry form and it has a very good shelf life. In the dry form, it has about 62% starch content. The cooked form, you will find the starch content is considerably less. So from the dry form, when you cook, it is very easy to cook, and as you cook, it takes in water, draws in water, and you get that nice softened texture. Apart from this, other examples would be boiling of sugar as in candies, and baking of dough we've already seen. Air drying at ambient temperature. Best example is your vadams, the sago vadam or jawarsi vadam as we call it. Here again, what we do is we subject the product to heat, and as a result the water gets removed and the resultant product that we get is a brittle product. Another example would be high pressure extrusion processing of ready to eat snacks. Now, I think you can all relate to the products that are displayed here. Now, in extrusion, what happens is the flour, the powdered flour, it is mixed with water. You first develop a dough. Then that dough is passed through or extruded through dies of rigid shapes. You have fixed shapes, you get different shapes in the market. So, when this process happens, as it is getting passed through the extruder, it is subjected to very high temperature and high pressure. The pressure is also very high. So once it exits the die into the atmosphere, the sudden drop in pressure as well as the conversion of water to steam results in the expansion of the product, and that's how your product gets cooked. That is also another example of food product where you can understand the role of glass transition. Apart from that, in certain products like your milk, the milk powder that you have, the process employed is spray drying. So dehydration by spray drying, you will find again that glass transition state of solids is attaining that glass transition state of solids is very important here. Now in spray drying, you will see that the milk is dispersed into very fine droplets and it is brought in contact with hot air. So what happens here is that the droplets are quickly dried. Not much time is given for the lactose to crystallize. If this were to happen slowly, then the lactose will crystallize. So this does not happen here. In freeze drying again, the same concept. Then you have agglomeration of food products. What happens here is you have your amorphous solids. It is first subjected to steam or fine mist as it is tumbling in the air. The idea here is to wet the powder so that they will adhere to each other and form larger granules. The idea here is to obtain larger granules, and it is done through agglomeration. So we have seen about glass transition temperature, how examples of food and how in food industry it is being employed. So if I have to give you a summary, I can say glass transition or understanding and studying glass transition is important for understanding the stability of food products. Food scientists and technologists measure glass transition, and along with this, the physical and chemical properties of foods and the water activity for studying and understanding the stability of foods. Apart from this, there are different techniques for determining the glass transition temperature. There are certain factors which have an impact on the glass transition temperature. These will be dealt in the following classes. Thank you so much for your time. Have a lovely day.